afternoon and good evening, everyone. Thank you for joining us. I would like to welcome everyone that joined for our second day of HPC training with AMD. This course is a collaboration between NCC France as part of EuroCC Project and CASTIEL project with great team of AMD. I would like to open the session and give the floor to our experts to introduce themselves and open the course. Thank you very much, and I hope you enjoy this course.
Welcome everyone to day 2, and we're going to go into more advanced material today, and we have quite a lot of content in our slides for today. Let me start with the sharing. Okay, so our first talk is going to be an advanced HIP. So we're going to dive deeper into HIP, understanding how to get performance out of it and understand what the compiler is doing with our HIP code. So we're going to look at kernel performance limiters again. We had some discussion of that yesterday and today. And tomorrow we're going to be looking at what is limiting performance of individual kernels and the application overall. So we'll look at memory bound and compute bound kernels and what you might do, latency bound, and then we're going to talk a little bit about the 300A architecture. So for GPUs, they are high throughput devices. So you really have to expose parallelism to use them effectively. And this is on the order of thousands of parallel work packages, work groups and work items for the GPU. And so as application developers, that's our primary job: expose the parallelism and then let the compiler and the runtime do the scheduling and make use of it. So if we don't have enough work, which quite often happens on small problems, the GPU is not going to be faster than the CPU. We're just not really using it well. So we want to really get full utilization of all the compute units on the system. So first of all, a little bit on performance limiters. And this is sort of divided into multiple categories by the arithmetic intensity. So if we have low arithmetic intensity, our memory units are going to be saturated, trying to load memory up through the cache system to the compute units. If we're compute bound, then it's going to shift to how you write the kernel to schedule instructions for the compute units. So it's hard to get a compute bound kernel on these GPUs and even on CPUs today. The machine balance is around 40 to 80 flops per double for typical machines today, and on the MI250 it is 128 flops per double. So it's really hard to get something to be compute bound. And so we talk a little bit today that flops are free, and that's a hard shift for us numerical people to really grasp that flops are free and all we have to focus on the memory movement. For applications which do not load memory in a friendly manner, cache-friendly manner, those applications are often latency bound. And I would divide these into those applications that are just not written to be effective at loading memory and you can fix, and those that there really isn't any way to avoid jumping around in memory. So let's look at what we do for these kind of kernels. So we've talked a little bit about the roof line and where we fall on this roof line for our applications. So if we're on the left side, we're bandwidth bound on the sloping roof. And if we're on the right side, we're compute bound. And we want to be as close to that roof as possible. And this roof line diagram is a very effective visual tool. Before this came out, we would often be citing what percentage of the compute bound peak limit that we were getting on a system. And people reviewing what our codes were doing would say, why are you only getting 1% or sometimes less than 1% of the peak performance of the system? And the reality is we were doing quite well, but we were bandwidth bound limited. And so this helps people understand that, our codes are actually doing well, but they're just bandwidth bound. Notice that the scales on this plot are logarithmic, so a small distance is actually a lot on this diagram. And you may want to adjust your roof lines when you look at them for your application. For example, peak flops could be using the matrix unit, or it could be using vector double precision, single precision, and so you don't want to compare it to a peak loading point performance that you can't achieve. So we have those unattainable regions, and then these regions where we get limited by bandwidth, compute bound, or poor performance is when we're below those lines. Let's look at the memory bandwidth. So reducing the data movement is still very important on the GPU as it is on the CPU. And though we can hide some latency on the GPU, it's still very, very important. So this is where we want to focus on how can we reuse data. The concept we really are trying to achieve is that we load data into cache and we use it as much as possible while it's in cache. We use all the values in cache. We reuse it temporal and spatial. So temporal means that the next loop, if we can reuse it by fusing a loop, that can increase our arithmetic intensity. Spatial reuse, when we do the next stencil tile, we reuse the data. So there's a couple of different ways to try to reuse data. It's not easy, actually. It's often hard to actually get effective reuse. Staging data in shared memory registers for faster access is a good technique. So we not only get it into cache, we try to get it into the faster memory. Lower precision has become very popular in recent days because we can move more data if we have a smaller data type. And so some of the considerations that we have on the GPU is to coalesce loads and stores to get that higher bandwidth. This is also true on the CPU with a vector unit. You want to get the wide loads. That's often even more important than the vector math. Getting the wide loads can be more important to improve your performance. And we try to avoid strided accesses, and we'll talk more about that in a couple of these talks, or a couple of the slides in this presentation. You can use vector data types that will help get wider loads, float 4, float 3, float 2. We can use non-temporal loads, so we can force the data to be written directly out to memory, to main memory, HBM memory. And there's an option to do that, and that frees the cache to store things that are more important. But the warning there is that it will not be in the cache for the next loop. And then aligned memory, just a second. So aligned memory access can help as well to avoid having to load more than one cache line. Here's a picture that shows these wider load instructions being used, and this tool is called Godbolt. You can go on the web and put your code in this tool, and it will show on the left the code you add, and then on the right it will show the instructions that are generated by the compiler. You can specify the compiler in this tool, and here we see the wider load stores show up with dword x2 and dword here. So we're getting different load instructions, dword x4 up higher. So that can be a key to showing that we are getting those wider loads. Compute bound. So it's rare to get compute bound. You need to do a order of 100 operations per byte loaded. And so large gems are usually the example of compute bound kernels, and gems will typically, highly optimized gems will be something like 60 flops per load. So they're getting up into that region. And even if you can't get to that order 100 operations, if you get higher arithmetic intensity, then one floating point operation to one load, if you can get 2, 5, that can make even that can make a difference in performance. So we can consider doing something like pre-computing values to look up. We have to balance that with memory loads, or could be more expensive than the computation. So sometimes applications will compute values on the fly to avoid the load. So you can go both directions on that. Watch out for math intrinsic functions. We want to be very careful that we don't get software versions of these functions. That's going to cause a lot more compute in the generated assembler. And a good example of that is the power function. So if you put the power function in C, the 3.0f is a floating point value. So that's going to be done in software, and it's going to be doing a floating point version of the power function. So it can be very effective expanding that out and just doing a times a times a instead of the power function in C. And if you don't like that expansion in your code, you can use a define or similar macro to make your code look a little cleaner. You can also use, for floating point, you can use packed FP32 operations, and that can really improve the compute performance. And float 2 can also cause that to happen. So we have a few different ways that we can improve the compute performance. So to get compute bound, we want to reuse data as much as possible, reading from registers or shared memory. So matrix cores can be a very effective way to get that compute bound performance up. And we have a blog post on that, how to use the matrix cores. That can take a little bit of extra effort, but you can use this ROCm library, WMMA, to help get use of those cores. So let's look at an interesting example with that is actually fairly common in code, where we're looking at this simple 4-line code, and it's expanding out to quite a bit of instructions. And what's causing this, if you look at the comparison at the left and the right, is that the constant 0.332 are all double precision values in this example, and the rest of the lines of code are single precision. The rule in C is that it promotes everything to double precision, so we see a lot of conversion functions happening in the generated code. It can actually be very helpful to pay attention to this and specify your constants with the right precision. Fortran, it's the opposite direction. If you are mixed precision, single and double, it's going to demote the values for the operation, and so you have to watch out going the other direction. Latency bound, you really want to have higher occupancy and increase the parallelism to give the GPU a way to do context switching while those loads are happening. And so, you can reduce the thread divergence and synchronization to help the compiler a bit to get better performance, and watching for register spilling to scratch memory. So the GPU just has an incredible lot of resources. And, the GPU, what is really amazing about the GPU technology is that it does a zero cost context switching. So it can hit a latency or a stall and switch to some other work if you have other work to do. And that's why we pay attention to occupancy and how much work we have for the GPU. And so that's what the concept of occupancy, and that's kind of a strange term for it. It really is just how much work do you have for the GPU versus how much the GPU can handle. And so we're looking at an MI210 here with 104 compute units with up to 32 wavefronts for each. So we're talking of order 3,000 wavefronts. You really, really have to have a lot of work to keep these things busy. And at some point, if you have enough occupancy, more occupancy isn't going to help. You've got something to switch to. Having more is not going to make that any better. It is true that, with various problem sizes, that maybe more of the small versus large problem sizes will get speed up on the GPUs. So here's an example of occupancy. If we launch a wave group with just one work group, it's just going to have one wave to work on, so there's no latency hiding there. If we make it 256 work items, now we have 4 waves, and we're keeping that compute unit busy, but we're not engaging anything else. And then if we have 1,000 work groups with 16,000 waves, now we're starting to get good occupancy. So that's the concept of occupancy. Have lots of separate work groups or waves for the GPU to operate on. And now with 16,000, it can switch to a different item to work on if it hits a stall. So we can have other things that stall the GPU, and that's memory resources. We often refer to this in terms such as memory pressure or register pressure, and that means we don't have enough resources for the GPU to use all the hardware. This is true even on the CPU, that there are a limited number of registers to use. On the GPU, we just pay more attention to that because we want to get that high throughput. So if you look at this diagram, we have this local data share, and it's shared by that whole compute unit. We have the vector, we have each of our SIMD units, and we have the vector general purpose registers. And the SIMD units can borrow registers from the other SIMD units, but that means that the SIMD units cannot be used or scheduled because there's no resources for them. It's less common that the scalar registers are an issue. And we also have the L1 cache on this compute unit. The L2 cache is actually shared across a couple units. So looking at the local data store, here we have the case on the far right where we're using 48 kilobytes of LDS per work group. And so we can only schedule one work group. If we reduce that to 8 kilobytes, now we can schedule more of the wavefronts on the compute unit. Register pressure. If we have higher usage of vector registers than 64, we're borrowing registers. If we have higher than 256, it will actually spill the registers to main memory, and that will slow the access time for those variables. It's not, even if you're spilling registers, that might be the best performance you're going to get for that kernel, but you do want to pay attention to that because it can slow down performance. If you can get below that spilling limit, then you might really improve your performance quite a bit. So, registers are scarce resources. GPUs actually have more than CPUs, but they are a scarce commodity. So looking at vector registers, we mentioned a little bit about this, that you have 64 for the wavefront, and 256 for the compute unit. And so if you use fewer vector general purpose registers, you can schedule more wavefronts. So that's what we usually look for, is can we get below a certain level so we can schedule more waves. As scalar general purpose registers, one value is shared across all the work items, so it's sort of like a broadcast of that value to all the threads. And there is a limited scalar register file. So here we have 102 scalar registers of 4 byte size. The compiler does the register allocation, and generally what the compiler reports is what you see at runtime. And one of the effective techniques to give you more memory resources is to reduce the size of the work group to allow more registers to be available. So on HIP code, we would use launch bounds and specify the size of the work group. Instead of 1024, the maximum work group size, we would use something like 64 or 128. So usually you can judge that based on how many lines there are in your kernel. If you have just a couple lines, then 1024 may be quite effective. If you got a 100-line kernel, you may want to get that launch bounds down to 64 or 128. The compiler does spill scalar registers to vector registers. This is not usually a problem, but don't take it as a challenge. I've seen some codes where, especially in C++, where they pass a struct of 100 values, flags and such to the kernel, and only use 2 of them, and then they find their performance is low because they're using too many scalar registers. There's a good blog about register pressure that you can look at on your own. So we can reduce register pressure a little bit, and that can make a big difference in performance. You're really restricted by what the compiler generates, so we try to nudge the compiler to use fewer registers. Some of the common problems are asserts in the kernel. Don't put asserts in. That's going to use up a whole bunch of registers. Mathematical intrinsics can also be a problem. And then the most effective technique is reducing the workgroup size. I have seen where, adding the restrict keyword will help the compiler generate more efficient code and reduce vector register usage. And some of the other techniques are more dependent on the compiler, and the compiler inlines functions and blocks of code. So it's difficult to get it to reuse a register that is used early in your kernel and have it reuse that for a later variable. You can play some tricks in your coding to force the compiler to reuse a register. Here is a really good technique to look at in your kernels. If you have 2 kernels in a row and they're loading large arrays of data and there's the same data in both kernels, if you just combine those 2 kernels, what we call fusing kernels, that reduces the amount of reads that occur. And you can just look at this and estimate the performance improvement. We can count the amount of loads that occur in the first case and compare it to the number of loads in the second case. And that will be effectively the performance improvement when we're memory bound. So thread block synchronization is a good thing to avoid. It's not as expensive as you may think, but don't overuse it. It does really limit how the compiler can optimize things. Host side synchronizations are quite expensive, and some operations, such as memory operations, synchronize activity. And the library and compiler teams play around with this a bit to, if you delay the free and do the garbage collection at some later point, there are pros and cons to that. So there's a limit to how much they can do to improve the situation. So you may need to manually do that. Moving memory allocations out of inner loops is really, really important. And on a GPU and a CPU, you can over allocate an array. If you do not touch it, it's in your virtual memory, but it never gets mapped to physical memory. And so over allocation is actually a good technique to avoid doing the allocations in the inner loops. Just over allocate it, and if you don't touch it, it isn't going to hurt you. But that may cause you to rethink how you're doing the algorithm. And you may need some code in there to catch if you're going to go out of bounds in an unusual case. Using asynchronous memory copies, you really want to use pinned host buffers. Pinned buffers versus pageable buffers usually gives you about a 2x of performance improvement because it doesn't have to move it from pageable memory to pinned before it can do the copy. That's true also with MPI. Atomics are something you really want to watch out for. Original GPUs only had atomics on integer values, and floating point values were added later. And people got, I call it lazy, but it's more, you could write code a lot faster if you just used an atomics rather than try to rewrite your algorithm in a way that didn't need atomics. So, but atomics can cause problems, particularly on the MI300 has slower atomics. And if we get contention in the cache line as well as on a single value, it can really slow the code down. Here's an interesting example of reducing thread divergence. These are short. This is a short thread divergence, so it's only a couple lines in the if blocks. The real cases that we worry about is when one thread may be doing 100 operations and the other is doing none. So, and this is by wavefront. So if all the wavefronts are executing the same code, it's going to, and if you have all short ones in that wavefront, it's going to exit early. If you have one long one, they're all waiting for it. In this example, we've got an odd-even pattern. And if we simply have each thread do both the odd and the even, we eliminate that if block. And we get more work per thread, which is generally going to be a plus. Usually one work item per, or one operation per thread is a little light to get the most effective use of a GPU. Warp shuffle are really a good way to get higher performance out of a kernel. We do have an example in the repository, though I don't have it in this presentation. But basically what you're doing is you're having the hardware in the LDS unit move data between registers, but it's not using the storage in the LDS. And so if you have a power of 2 width, you can do this operation and speed things up quite a bit. There's allocations matter quite a bit in performance, and some of them cause more work at allocation time, and others cause more work on access. So we have this MI300A, and it's got a single pointer to fit the same physical memory, but we still have to load the cache system for that. For the MI300A, we recommend HipMalloc. It's going to populate the device tables, and the CPU also knows about it. So that usually works quite well. The hip host malloc is sort of a host side allocator, but it's also going to register the memory on the GPU. Malloc is only going to register the GPU on first touch on the GPU. Page size matters. Most of these systems should be set up that the CPU in the MI300A is also set to use 2 megabyte pages. System allocators by default go to 4 kilobyte pages. The GPU uses 2 megabyte pages. And so by configuring the system to use for the CPU to do 2 megabyte pages will help a lot. With 4 kilobyte pages, you can only address about 16 megabytes of memory before you have to do a page lookup, and the page lookup takes hundreds of cycles. So even on the CPU, forcing the system to do 2 megabyte pages can have a performance benefit of 15% to 2x performance improvement. And then we can change what resources are being used for copies. So especially for the MPI, we can either use the SDM engines, or we can create basically a HIP kernel to do the operation that can get higher performance. And we can also think about how to improve performance on the CPU, because that often becomes the bottleneck as we speed up the GPU. So this gives you a quick overview of kernel performance and limiters. And I believe we're going to go into some examples here. So the examples that you can do it during the exercise portion. And I'm going to skip. So here we're showing how to output the usage by that the compiler generates. I'm going to let you go through these slides to look at it, but you can cause the number of vector registers to change. You can do that exercise. And a lot of these, what the kernel usage is for these resources, there are a lot of ways to get that out of the compiler. I'm going to give a quick example of transpose because we're running close to our time limit here. But this is going to look at coalescing data and coalescing data loads. So this is a deep dive. This is a more advanced example. And so what do we mean by coalescing data? Well, if we have contiguous data that the adjacent threads are all accessing memory that is within a cache line, the GPU will just do one fetch to coalesce that memory read or write. So that can greatly optimize the memory movement, and we can also have fewer page loads. So here, that's just stating that on this slide. So we're going to reduce the number of cache lines that have to get loaded. If the data is scattered, we're going to have to do multiple cache line loads. Once it is in the GPU, it's faster, but the cache line loads are the bigger limit to performance. So we want to get rid of that limiter. So we often term this cache line load limited. It's not just the data values that is loaded. It's really if we calculate the cache lines, that's the important parameter. And so if we use unit strided access per thread, we're going to get better performance. Here is an example of structure of arrays, an array of structures, and structure of arrays generally does better because if we access X in this example, it's going to use every third value of the cache line if we're doing array of structs. So the only time the array of structs is effective is if we always use everything together. So generally structive arrays is a better way to set up your data structures. We can align data, particularly with structs. If we pad the array, we can get the alignment to be on that a larger alignment and that will let us get more effective memory loads. So, and if we have misalignment, it may require an additional cache line load. So you may need to add one cache line. So it'll give you a small penalty. It's not horrible, but if you can improve that, that will help. Strides greater than 1 are quite problematic for the GPU. You're going to be accessing a different cache line with every thread. So you can do things like for 2D calculations, you can do a transpose to get everything lined up the way you're going to access it. For example, for an FFT, you can use a structure of array, stage data, or pad a line and use vector loads. So there's a few different ways you can improve that situation. So on LDS banks, they're a different kind of memory. They're banks of memory. And for those, contiguous memory access is not as important. What is important is that we don't access the same bank for multiple requests. So we can offset the data access so that we're not accessing the same bank. We're going to show that in this example. And for performance, it's typical, the typical pattern to improve the performance is to use a tile. So we create a tile and load it from global memory with coalesced vector accesses, store it to LDS. Now we avoid that bank conflict in the accessing data out of the LDS, and then we write back to global memory in a coalesced manner. So we're going to show that in this example, and you can run this example during the hands-on. So there's multiple vectorized loads that you can do, and that can be very, very effective. The disadvantage here is that you have to handle the tails if the length is not divisible. I have seen in some libraries where they will actually test if the array is divisible by 2, use a double 2 kernel, else use the single double kernel. That may not be as attractive to do in your code, but for library codes, that can make a big difference. So using restrict, align as, that can help, and assume align can give the compiler more information. So in this transpose example, we're first going to do a transpose read and contiguous. That's what you would usually think about when you're writing code. And so memory is laid out in C order fashion. In fact, we are allocating it with a 1D memory allocation and passing it into the kernel and creating the memory, 2D memory indexing. So it's going to have the X dimension varying the fastest. In this example, our input, we're going to load it as 0, 1, 2, 3, 4, 5, and the output will be 0, 3, 6, 9, so it's not going to be contiguous. We define a macro to make it more obvious what's happening here. And so if you look at this bottom line, you see output of XY equals input of YX. X is varying fastest, so we have a contiguous pattern on the input, and we do not have the contiguous pattern on the output. Let's see the code for this, and then see what the performance looks like. So this is a quick transpose kernel reading contiguous, and you can build this code, go to the example, build it, and run it on the MI300A. I'm going to show it to you for the MI210, and the 300A is actually has twice the cache size, and the cache lines are twice as long, so it improves the performance quite a bit relative to the theoretical bandwidth. So for this one, we're getting 4450 microseconds for that transpose. So if we make it write contiguous, we change it so that the output is, the X is varying fastest. So the output will be 0, 1, 2, 3, and the input will be 0, 4, 8. And let's see what happens, what the code looks like, and what the performance is. And you can look in more detail at during the hands-on at this code, and you can see that the values are contiguous on output. And by doing that, we reduce the time to 2,900 microseconds. That's quite a big improvement in performance with just a little work on the kernel. So we talked about this idea of how we could do contiguous memory reads and a contiguous memory write. And so we pad that LDS tile, we're going to load it, and we're going to add that padding on the indexing so that we're not accessing the same bank. We have to do async threads after loading LDS. We do a few minor things like restrict and const, although I don't think they really make a difference in this case. And we use the same integer type for the comparison variable so that we're not doing an unsigned versus a signed, which requires the compiler to add instructions. Our tile size we set to 32 by 32 because our workgroup size is 1024. There's other tricks to do that you can do here, but this is the simplest approach. So we load this LDS memory here in between setting up our source thread and writing out our output threads. And I think there is a bug in one of these codes in the slides, but not in the example. So we swap the order for reading from the tile because it does not create that coalesce memory issue. The tile uses bank memory access. And so what happens performance-wise when we do this one? We get a slight improvement over that output contiguous result with 2,600 microseconds. And if we look at all three of these, we see that we've gotten almost a 2x performance by working on this kernel. Now you may think that, oh, I should always do write contiguous if I'm only going to get one of them contiguous. But this example was had a fairly balanced read and write. If we were reading 10 variables and writing out one, it might be better to do the read contiguous. But in both cases, the tiled is going to be better. So think about this if you're doing 2D or 3D stencil operations or similar, you can improve the performance and operate on that LDS memory in between the read and the write. So this was on a MI210 with ROCm 641. We did this exercise previously in a workshop and got very, very good results out of the MI300A. So I leave that for you to look at. I think with that, we're done with that presentation. Just a little over. So I'll check the chat for
There's a couple
questions.
of good questions in the chat. They're a bit
Uh-oh.
long, so I might have you just read them.
Okay, I'm looking at it. So yeah, these are good questions. So on the CPU, it's actually similar. If you have two threads writing to the same cache line, that's, yeah, what we want to, so this comes back to why was the write contiguous faster than the read contiguous? And the reason is that on a write, you actually have to load the cache line, then write into the cache line, and then store it back out. So you're doing both a read and a write with each write operation. And if you're not careful, it can cause it can cause what we call cache thrashing. So if it gets pushed to main memory and another thread is using it, it's going to have to refresh the cache. And on the CPU with threaded code, that may cause a lot of this cache thrashing that kills performance. But if you do it right, it's actually quite effective to do all those writes into the cache line. This is one of the ways you can use the hardware threads to operate on the same cache line, but you don't have as much control on the CPU. So if an adjacent thread, which is on a different compute, different core on the CPU is accessing it, you're going to get this cache thrashing. So yeah, it's a little bit different on the GPU effectively, although the basic mechanics are the same. And this is one of the advantages of the GPU versus the CPU, and why we often get on the GPU much closer to the theoretical bandwidth performance. And Cocos actually does try to flip the data ordering, and so sometimes you can just have your data laid out in the right order, and quite often I will find this on code that people haven't been very careful with. They'll be striding through the data when they could just change the layout or the order of their loops. Compilers will sometimes flip the loop order on better compilers, but you can always do that flipping in your code and you will get better performance across all the compilers. So that was one of the things that Cocos really cites as a big benefit of their tool, is that they can have a different layout for the CPU versus the GPU, and they do it automatically for you. But you also have a lot of control on the layout. If you're playing around with the layout, I suggest using a macro so you can switch between the layouts and test it before you change all the accesses in your code, because that can be very painful to just find out it's not really any faster to swap the order. Yeah, and one of the problems is that, yeah, in an ideal case, you can change your programming to be to access the data in the right order, so the compute is accessing in the same pattern that it's laid out in memory. But then you go to the next kernel and there's no way it's going to access it has to access it most effectively in the other order. So you can't always get every case to be ideal. And that may be where you even consider the idea of swapping the data structure if you've got a lot of accesses in the next block of code. For pin memory versus pageable memory, pageable memory can be paged out to memory. That's one of the virtual memory capabilities that has been added to computers early on to enable us to, let's say, run an Excel spreadsheet, then run Word. We'll swap out Excel spreadsheet so that we can effectively use its memory. But the problem is that for network cards, MPI, you cannot send that pageable memory because it might move during the operation. And so we have pinned memory, which is not allowed to be paged out. We have a limited amount of that, and it's going to prevent this overuse of memory, this virtual memory concept that's built into kernels today. So by putting things that you're going to be transferring between the GPU and the CPU over MPI, other cases like that, and put those into pin memory, you can get 2x performance boost on your on your data movement. So I hope that's answered those questions, and we can put more detail in the chat. So I think we have gone through the exercise scheduled time here with our discussion. Please take some time to do those exercises as you get a chance. And I think we move on to advanced OpenMP and test Giacomo's voice out for today.
Yeah, sorry everybody, my voice is a little down today, but we're gonna make it. Thanks a lot, Bob, for your presentation. And let me go ahead and share my screen. Let me also check first how much time I have for this presentation. Okay, that's enough, I think. Okie dokie. All right, is it coming through?
It's coming through. Let's get full page.
All right.
There it goes, and we can hear you. Take it away.
Okay. Thanks, everybody. Great to be here for one more exciting day. So the next presentation is gonna dive pretty deep into OpenMP, and it's gonna build upon what Johanna showed you yesterday. And we're gonna add quite a lot of detail to that content, okay? So just to kind of recap what we have discussed yesterday, when you are trying to use OpenMP to offload your computation to the GPU, you have to keep in mind that the process is in a way twofold, because first you're gonna have to move to the GPU, and then the next thing that you should be doing is you'll have to parallelize appropriately your code so that not only it executes on the GPU, but it actually does that effectively and in a performant way. So you can see this as being divided up with basically two main directives, I would say. One is pragma-OMP target, which basically moves your code, the lines of your code that come right after, to the GPU. And then, as you've seen yesterday, you can see the loop construct as what actually makes the computation parallel and performant. However, loop is a fairly new construct that is not completely portable across all compilers. And therefore, even though it's convenient to kind of see this as just this procedure made of two steps, the target and the loop, right now, the loop actually needs to be kind of made explicit. We have to look behind the curtain. And that, as you've seen yesterday, basically leads to having, after the target, the teams distribute parallel for or parallel do. So yesterday, you've seen that if you just do pragma-OMP target, as we've said just now, you're going to be moving your code to the GPU, but your code is going to execute serially on the GPU. So there's just going to be one thread doing all the work, basically. But you can start using the hierarchy of the GPU hardware, having the teams construct follow the target. So basically with pragma-OMP target teams, you will create a so-called league of teams. So there's going to be multiple teams, each composed of only one thread at the moment, that will execute your code. But at this point, you have to be careful, because if you just do pragma-OMP target teams, you'll have multiple teams, each of which is composed of one thread only, but they all execute the same code. So you're gonna have a race condition there, because you're not partitioning your for loop iterations. Each of these threads gets them all, and so they're gonna step on each other's toes. So the code will run, you're not gonna get an error, but the solution will likely be inconsistent. And so now that you have learned about OpenMP and HIP, basically the teams for OpenMP correspond to the work groups for HIP. So the next thing is to add the distribute, which basically will take chunks of the for loop that you're trying to parallelize and port to GPU and distribute those to the teams. So in this case, you'll have multiple teams, each composed of only one thread, and that thread gets a chunk of the for loop iterations, so that will still be parallel, will not be the best parallelism you can get, but it's a certain kind of parallelism. So the solution will not be negatively affected, and you'll have some parallelism. The next thing to do is to add the parallel to this. So Pragma MP target teams distribute parallel. The parallel will basically create multiple threads. So you'll have multiple teams, each composed of multiple threads. But if you stop here, you'll have that, you remember the chunk of iterations that each team received will be given to each of the threads in the team if you just use parallel. And so even in this case, you may have a race condition. What you need then is the for, which will spread those iterations that have been given to the team among the threads in the team. So I know that it's not super easy to familiarize with this idea, and that's why we're going to have a few examples next. But this is how you leverage the hierarchy of the hardware with OpenMP. And this slide here is basically just telling you the syntax. So for each of the directive that I described, there's a way to do it in C or C++, and in Fortran. Notice that in Fortran is generally good to also include this AND for the directive because with C and C++, you can use the curly brackets to tell the compiler where the code that needs to be affected ends. With Fortran, you don't have that. So if it's just this, if it's obvious to the compiler, then you don't need to include this end. But in general, I mean, if you do it, it doesn't hurt. It helps the compiler. And in some cases, actually, you will have to do it. Okay, so now we're gonna take a look at what I have just described in even more detail. So basically, we're going to consider this simple SAXP kernel in C++ that we're trying to offload to the GPU, and notice that we are using pointers here. So you've learned yesterday that with C++ and pointers, those are not mapped directly to the GPU. So as it says here, you either need to add a map clause to move them to the GPU, or you need to leverage unified shared memory. So this is our starting point. See that the directive that we're using is the full meal here. It's the whole thing. So this is offloading to the GPU and leveraging all the parallelism. And now we're gonna show you what happens if we just use a subset of these. So this is our baseline. And notice that we are exporting this environment variable that we mentioned yesterday as well, libomp target kernel trace, and we're setting it to 1. And that will result in having this information outputted to the terminal. See that we're getting the number of teams, the number of threads, we're getting LDS usage. So yesterday there was a question about LDS usage. You'll see that the compiler is handling that for you. And in this case, it decided to not use any, so there's 0. And then it tells you the count of scalar registers, vector registers, whether there's been any spilling. Bob just mentioned the register spilling for the heap talk. And then you'll get the timing. And if you use the newest compilers that are in the ROCm AFAR modules, you'll also get one more piece of information here about occupancy. Okay, so this is our baseline. The time of the kernel with the maximum parallelism that we can leverage is 0.082906. Okay, so see, the next one that we look at is just pragma-OMP target, which is just moving that SAXP to the GPU without doing any parallelization. So it's just going to be one thread in one team doing the whole thing. And you see that the time of the kernel is a lot larger. Then we're using teams. So here you see that it actually becomes worse, the timing, because we are basically doing the same work that we were doing with pragma-OMP target, but just multiplied. There's just more teams doing the same work. And plus, as I said, this will lead to inconsistent results because threads will be stepping on each other's toes. pragma-OMP target teams distribute actually brings it down by a lot. Notice here that at the bottom of the slide, there's the reference. So the best that we can get is 0.082, and here we got 0.14. So that's already pretty good, not the best. And if we look at pragma-OMP target parallel 4, that just means that you're using one team with multiple threads on the GPU that have been distributed the iterations of the for loop for the SAXP. So this is also pretty good, but not the best. Okay, so the next thing to discuss, and we're gonna be moving away from the analysis of the subset of the pragma now, is the collapse clause. So the collapse clause is useful in case you have nested for loops, because basically what you'll do is like you'll tell the compiler that those iterations from the two nested loops can be distributed as if it was just one big for loop, loosely speaking. So here you see on the right, if you have this for loop over j and 1 over I, with the collapse, you're letting the compiler distribute each of those, the iterations coming from both loops across your hardware, basically, instead of having to do one first and then the other one. And then, yeah, this is just so that one was a C example. This is a Fortran example. Collapse 2 means that there's two for loops that you're trying to collapse. Okay, so something that's worth mentioning is that, you've seen that kind of like a magic spell here that pragma-OMP target teams distribute parallel 4 should go all together for better performance, but it's in some cases, it might make sense to split it up so that you first call the pragma-OMP target teams distribute and then the pragma-OMP parallel 4. So, in general, it's better to let the compiler handle that for you, but this might be a good thing to do in case the outer loop is like really small and there's not a lot of distribution that makes sense doing there. So here you see in this case, the loop over J will just be distributed among the teams, and there's only one thread at that point. So each single thread of those teams will get some of these J iterations, and then the execution over multiple threads is just done on the I loop here. So, in this case, maybe n is a lot smaller than m, and so one might want to be doing this. But as I said, in general, it's better to let the compiler handle this, or as we've seen, you might want to use the collapse clause instead. But this is something that it's available to you if you want to test it out. Okay, so in terms of other compute clauses, so we're gonna go a little deeper now. And you've seen with heap that you have quite a lot of control on the way you execute your kernel, the way you set up your thread grid. With OpenMP, at least initially, you don't see that, and that's probably one of the reasons why maybe approaching it is easier in a way, but there is some control that you can get with OpenMP as well on the thread grid hierarchy. And Johanna yesterday was mentioning that LDS customization or usage customization is also coming soon. But what I'm showing you here is that you can use these clauses here to go and kind of interfere with the compiler's plan on how it's gonna distribute the work. So for instance, you can specify this num teams clause that will tell the compiler how many teams you want, which is basically the number of work groups that you'll have with HIP. Or you can also specify the number of threads. So this would be the workgroup size and the thread limit. So the thread limit is an interesting one to use because we've seen oftentimes that just that alone can improve the performance of your kernels with OpenMP quite a bit. Because for instance, among other things, it can reduce register pressure and therefore already benefit your application runtime. Something that is very important to mention, I think, is that you have this option for the no wait clause. So you may be wondering, why should I not wait and why is it there? Well, you know, we talked about HIP and we said that HIP kernels are non-blocking for the host. On the other hand, with OpenMP, there is always an implicit synchronization barrier at the end of your kernel. So if you don't want the host to wait for that kernel to complete, you'll have to include this no wait clause. And it's my personal opinion that OpenMP is great, but you still have to be aware of some of its default behavior to not be surprised by it. And this is part of that default behavior of having an implicit synchronization barrier. We've talked about the collapse, and for the reduction, I'm gonna skip it for now because we have dedicated slides just coming in a second. Okay, so if you are wondering what's the difference between num threads and thread limit, here it is. So thread limit needs to follow a team's directive. So see here, we have a case where we have split that pragma line as I showed you before, and if you split it, then the thread limit has to go after the teams. If you put it after the parallel, you get an error. And on the other hand, the num threads needs to go after the parallel. If you put it after the teams, then you'll also get an error. So you know now that with ROCm info, you can get a lot of information on your hardware. And the next question is, you know, I showed you how to get control on your launch parameters, but which parameters do I pick now that I can kind of mess with them? Well, so with ROCm info, you can get the number of compute units in your hardware, and it's normally a good idea to have the number of teams be a multiple of the compute units. So in this case, we're selecting 220. And for the thread limit, so the workgroup size, you already know that is good practice to set as a multiple of the wavefront, which is 64. And then if you multiply num teams by thread limit, you'll get the total number of threads, basically. Okay, so the next one up is a bit of a biggie. We're gonna be discussing the idea of regions in OpenMP, which is fundamental when it comes to, for instance, data management in terms of just where it sits. Is it on the host or on the device? And in general, regions can be defined just as those parts of code to which the pragma applies. And in general, what you can assume is that the region to which the pragma applies, just the block of code that comes next. But you know, in C++, for instance, when you have classes, that is not the case anymore. So we'll be distinguishing between data regions that identify basically where the data sits, target regions where the computation happens on the GPU, and then parallel regions where the execution happens in parallel. So initially, OpenMP was handling mostly structured data regions. Those are basically the ones that you can just enclose in curly brackets. But to facilitate using OpenMP with C++ classes, then the concept of unstructured data region has emerged as well. So going to a visual example here, so a structured data region would be something that you can enclose between curly brackets. An unstructured data region is a region where basically your data exists in, and it's not necessarily something that fits within curly brackets, such as the scope of an object from a class, for instance. So here we're giving you already a big spoiler, but that's okay. So we're gonna be talking about Pragma OMP target data for the structured data region, and Pragma OMP target enter data and exit data for the unstructured. By the way, this doesn't mean that you can't use the enter data and exit data for the structured, but you cannot use the target data for the unstructured. Okay, so you've seen the maps yesterday with Johanna, so you know that the map clause is what you would use to move your data from host to device. And remember that one of the unwritten rules, well, it's written, but let's say the implicit handshake with OpenMP is that you always think of it going from host to device. So the to always means from host to device, and the from always means from device to host. So you have to keep that in mind. So yeah, so you've seen the maps yesterday, and what you haven't seen yesterday is the map types. And also, I think we haven't looked in target update in a lot of detail either. So you can, okay, yeah, you've seen the map types, but not all of them yesterday. So you've seen the to and from. So to and from, as I said, just copy the device from host to device and or back. And what they do is they check if the memory is already allocated on the device. If it's not allocated, they allocate it, and then they set the reference counter to 1. If it's already allocated, then they just check the size and increment the reference counter. There's also an important type of map, which is the map always, which will always copy the memory even if already exists. So one other default that needs to you all need to keep in mind is what I just said, which is that the map only copies the memory if it doesn't exist on the device. If you want to force a copy, then you need to add the always. Map alloc delete checks if the memory is already allocated. If not, it allocates it. If it's already allocated, it just increments the reference counter. And the update to from basically is what you would use to, well, I think it's kind of self-explanatory to update the data either from host to device or from device to host. And notice that the update does not modify the reference counter, and I'll show you that in a few slides. Okay, so the target data is a construct that you'll use to create a data environment. Because remember, the whole point of this is that, yeah, I mean, you could use the maps on any pragma that you have, But the big deal with GPUs is that moving the data is expensive. So you don't want to be moving data from CPU to GPU all the time because the performance is going to be subpar, let's say. So the idea is to keep the data on the device for as long as possible, for as long as you need it, and then move it back if you need to. So the idea of these data environments is that you let the data sit on the device for as long as you need it, so that you don't have to copy it back and forth between GPU and CPU. So the target data applies to a structured block of code, and it looks something like this basically. So you'll have your arrays here on the host, and then you use this PragmaMP target data to have them exist also on the device. But the important thing to remember is that unlike the PragmaMP target, the PragmaMP target data does not move your code to the GPU. So whatever happens after this PragmaMP target data is still on the host. So this has to be remembered because it's important. And next, you see, we are calling a bunch of functions here that offload to the GPU, but we don't have maps there because they sit inside the data environment provided by the target data. So the arrays that they used have already been moved to the GPU, so you don't need to have a map there. For what concerns unstructured, oh, sorry, actually, I should mention something very important for the target data map. You see here, we're doing a map to from for C. So because it's a map to from, it means that at the end of the data environment, whatever is on the host for C, it will be overwritten by whatever is on the device. So if you are modifying C on the host inside the data region, in the data environment, that will be overwritten by what you have on the device. So this is very important to keep in mind. For the unstructured data region, we use target enter data and exit data. And with target enter data, the from and to from types for the map are not allowed. If you want to force the copy back to the host, on the exit data, you'll have to do a map from. So as we've said before, these constructs are used to facilitate the use of, for instance, C++ classes, but you can also use them on a structured data region, as you've done with the target data in the previous slide. So this code here does not exactly do the same thing. Because you see here, we're just doing an alloc for the map, whereas before we were doing a to and to from. So it's not exactly the same thing, but this is just here to show you that you can actually use this also on structured data regions, not only unstructured. And for the target update construct, I already spoiled it, so I don't think there's a lot to say about it that's gonna add more. But I wanna show you this example here that puts together some of the ideas that we've discussed right now. And most importantly, on the right side here has these bars that basically tell you where the code is being executed. So it's important to keep that in mind. So we have this target data that is creating a data environment for this structured block of code. So that is allocating TMP on the device, mapping input to the device, and then saying that as soon as we get out of this region, res will be copied from the device back to host. And see, this is on the host. So as soon as you get to the next line, you're still on the host. But then we have this kernel here that offloads to the GPU. So we'll be on the target next. Right after that one, we'll still be on the host. So see, we're doing some stuff to the input array that's going to modify it. But because it's used in the next kernel, we want it to be up to date. So we do a pragma-mp target update too. And this is still on the host. Then we find the kernel. That's gonna offload this computation to the GPU, and then right after that's done, we're back on the host. So yeah, this is just a review of what we talked about. I'm gonna skip it. And you now know enough about OpenMP to have a lot of questions, I'm sure. And as you learn more about it, you can probably already tell that there are going to be some tricky situations such as structs or classes. And we do have some examples in our examples repo that hopefully can help you clear out some of the confusion that arises. But we're going to be looking at more in the next slides. So you can, for instance, be in a situation where you have an array that has a statically decided size, but you may want to change that so that it's dynamic and specified as an input. So in that case, you're gonna leverage the enter data construct and do an allocation on the device. And similarly, if you have an array that's part of a struct, still you might want to use the enter data map to move it to the GPU. And then whether or not you use release or delete at the moment is not super clear because we've seen that the behavior may change, and in some cases one could delete, for instance, the whole struct, not just the one pointer that you wanted to delete. So you have to be careful there. Okay, so now we have talked about libOMP target info before in the profiler presentation yesterday. You'll see now what kind of output it can give you. So you've seen libOMP target kernel trace that gives you information on the launch parameters, the thread grid, and the occupancy if you're using the latest compilers. libOMP target info basically is what is gonna let you pull the curtain and you're gonna see everything that happens behind the scenes. So get ready for a lot of information, especially if you set it to -1. You can just output a subset of the whole deal of information that you get by setting it to some of these other values, for instance. And if you just want to restrict the amount of information that you'll get, because as I said, get ready is a lot, you can use this this routine here. That's basically something that you will put before and after a specific directive that you want to unpack, and then the output of libOMP target info will just focus on that, so you won't get all the directive information. Okay, so we're gonna focus on this example here that's in our repo, Pragma examples, OpenMP, CXX, memory pragmas. This is your usual SEXP. And basically what you have to focus on is this line here, the directive that's doing the usual offload to GPU with parallelization. And we have a map that maps X and Y to the GPU and Z from. So X and Y are just two because we're not modifying them on the GPU, and Z is just from because we just need to read it back. Notice that we're not mapping A because A is a scalar, so it's already mapped by default for us. Okay, so here it is. here is the whole output that you get when you set libOMP target info equal to -1. So you see that basically you just pull the curtain here and see everything that's happening behind the scenes with OpenMP. So it's telling you that you're entering the kernel with 5 arguments. It's telling you everything about the types, the maps, you see. And as I was telling you before, the scalars are mapped implicitly as first private, so you don't need to map either A or N. Then you see that the device memory is allocated and the reference counter is incremented. This is for Z. You've got X and Y as well. New maps are created for X and Y. There's information on the copy here, copying data from host to device for Y and X, since that's what we wanted. And then if you just, there's a lot more info that you can see here. There's info on the launch of the kernel. It's telling you that information that you've seen with the kernel trace. And then at the end, it's doing the deletion. So this is a lot of info. You kind of have to be prepared to what you're going to be seeing. And now there's a couple of versions that we're going to look at. For instance, there's a version 2 where we are including the always to the map. And so the output that you see with sorry, yeah, we're including the always, but we're also including the data environment. So instead of having just the map as we had here, we are using the target enter data and target exit data. So basically what you'll see in the output is the creation of the map entry, and then the exit data outputs here where you remove the map entry. And we are doing the always here because we actually do need to copy that data to the device since we're using it. See here, we're just doing an alloc for X and Y. So if we didn't have the always, then the copy wouldn't happen. But we need X and Y to have certain values because we're using them in the SAXP. Another version here is one where we are using the update to right before the kernel. So instead of the map, we're using the update to for X and Y, and then the update from for Z. So remember, initially we had map to XY, map from Z. Now we remove those maps and instead we're using the target update. And what I want to show you here is that the reference counter is not incremented with the update as we expected. So see here, this is the reference counter with the first update, and this is with the second, and it didn't change. Yeah, so we've got another version that is using the delete instead of the release. I believe. Sorry, no, it's using the release instead of the delete. So here there was a delete. Here there was a delete in the exit data map, and version 4 is replacing that with a release. Okay, so the next thing to talk about is reductions, as I promised. So the reduction, as I'm sure most of you already know, is the operation where basically you are, as the name suggests, reducing the size of an array to something smaller in general. Most of the times it's just a scalar, so maybe you're computing the norm of something, or there's a computational physics code that's evaluating the contributions from a gradient, say, and then you are adding those up. There's many uses of a reduction. So you can do that with OpenMP. And here there's 2 lines in green and 1 in red. The green ones are what you should be doing. The red one is what you shouldn't be doing. And let me just go through those real quick. So the first green one is the data environment that we've seen with the target data map. And the second green one is the kernel offloading, where we are specifying a reduction. So see, reduction plus means that we want the plus as operator, and sum is the reduction variable. So you don't need to map sum to and from, because that's gonna be done by OpenMP for you as a default. So this is another default you have to keep in mind. You don't need to map the index of the for loop as private, because that's already done for you by default. And you shouldn't actually even need to initialize the sum to 0, which is your reduction variable. But since it's needed for serial code that's that is not compiled with OpenMP, then we just keep it for portability. And you can also, so this was a reduction to scalar. So some here is a scalar, but you can also have reductions to array, and you can do that as well. You just need to basically specify the size of the array when you specify that as your reduction variable here. So some C has a J now. Okay, so the next thing to discuss, I know it's a lot, we're almost done. The next thing to discuss is how to call functions from target regions. So here you see we have this function compute that is called from inside the target region, so from the device code. And we have to talk about it because whenever you want to do that, you need to tell the compiler that it has to create a version of that function for the device. So there's ways to do that depending on your programming language. And the standard has several options that are approved, and different compiler vendors may not implement all of them, so they may just do a subset. And for our compilers at the moment, the ones that are circled in red are not implemented. But this is what you would be doing to create a device version of your functions to be called from a device kernel here. So there's several options for C, and at the moment only one works with Fortran for our compilers. And you can also declare data to be on the target. And the color coding here is the same as in the other slide. But let's take a look at some clauses for the declared target. In particular, I want to focus on this device type here that basically you can use to build just a host version or just a device version, depending on what you need. And then there's others that we're not going to be looking in detail during this presentation. So there's examples for these that you can find here. And these are the examples that I'm gonna describe in the next few slides. So, if you wanna browse them on your own at your own pace, you know that you can find them here. Okay, so for the case of C here, I'm basically showing you on the left just a CPU version. On the right, something that we're porting to GPU with OpenMP. And notice here that there's this compute function that it's called within this for loop. So we have added this directive to offload that loop to the GPU. And the next thing we have to do to make sure that compute is seen from the device code is to add this line to the function definition here so that the compiler knows. We've seen that with the AMD Clang compiler, you don't need the begin. So here you see we have the Pragma OMP begin declared target. You don't need it with our compilers. If the end directive is not present, then you'll get a warning like this one here, expected Pragma OMP declared target, Pragma OMP end declared target. So the next thing is what happens if you have global data. So here you have this constant that's defined on a separate file. So it's declared as extern. We're gonna be using that inside the compute function. So you'll have to put this Pragma OMP declared target before and after the extern declaration. And then you have to go in the separate file where there's actually the definition of that constants array and slap an OMP declared target there as well. Okay, so the next one is with Fortran. So on the left, we have the CPU version. On the right, we have the one that we ported to GPU. Notice that here there's the Fortran array syntax to initialize X that we are replacing with a do loop because that has been added recently. Sorry, this note here is not visible, but it's been added. I think it says OpenMP version 6 for the specification added that. But this is so that it's more portable. And then, as you've seen before, we're going to have to include this OMP declare target on the definition of the compute routine so that it's seen on the device. Now it gets a little more complicated because we're going to be looking at C++ with classes. So here, this line pragma-OMP requires unified shared memory is commented, but actually it shouldn't be commented, since you see down here that we're not using any map for X, so we need that. So we have a class here that's called science, and we have our main program that sits in big science, and the compute function is a member of this class science. So that's the extra complication here that we're adding. And basically what we do is nothing in this case other than just what you have seen here. And that is because methods that are defined in the class are inlined into the calling side. So in this case, you don't have to add any pragma line to that compute function here. However, things change in case you have an external member function. So before we had this compute that's declared like that. So see here, the difference now is that before we were defining the function compute from within the science.hh file, so we didn't need to do anything. But now we have a separate file that has the definition of the function. So see, this was the header before that had the definition of compute. Now we're just declaring it and defining it in a separate file. So in that case, we actually have to add the pragma-OMP declare target. Next up is the situation where you have virtual methods. So you have a class inheritance. So we have a new class that's called hot science that is inheriting from the base class science. Once again, we need the pragma-OMP requires unified shared memory as before. So see here, what we do in this case, this is our separate file where we have the hot science member functions. So, sorry, the separate file is hot science member functions that is defining those functions, so the compute. So as before, we do add the pragma-OMP declare target there, but then we don't need to add it to the base class. So we just need to add it here. Okay, yeah, so it's been a lot to chew. I understand that. And this is just a note that's basically telling you that you should use the latest version of the compiler for increased functionality, and that vendors may implement things a little different. So even though there's a standard, it's not always the case that it's respected, super strictly. And this is just a note that with ROCm, you have an implicit declared target that you can leverage in case your function declaration and definition sits in the same file where it's called from the kernel. So in a situation like this that I'm showing here, you actually don't have to include the declared target because there's an implicit declared target in this case. Okay, so last few slides on OpenMP optimizations. These are gonna go a little fast since I'm using up a lot of your time already. So you already know that you should be reducing the data transfer between host and device. And we have seen that with the data environments. So that's one way to do that for sure. And obviously that's more important on discrete GPUs, a little less on MI300A because it has the unified memory space for CPU and GPU. You should move the memory allocations and frees out of the inner loops as much as you can, because you may unintentionally cause some serialization and synchronization issues that you may not be aware of. And we've got some examples here. You see Pragma examples, OpenMP, optimizations, allocations, where you can see the benefit of taking this out of the for loops. You can use memory pools. We've got examples of that in our repo as well. There's one very good example done by Johanna that actually sits in the rockprov v3 directory, because that example is using so many things that we couldn't decide on what was the right directory to put it in. So it's not in Pragma examples, it's in rockprov v3, but I recommend you check it out. And it's using the umpire library to use memory pools. And the last thing to mention is that you should be setting large page sizes, because that helps for performance. And you have to basically check that if you're specifically, for instance, on MI300A, that's already set for you. And that's because with heap_malloc, you will already get with heap_malloc, you already get the large size, but with malloc, you don't by default. And so with 300A is specifically important. I'm talking about OpenMP and I mentioned heap_malloc, but it still applies if you use, for instance, the OpenMP API to do allocation on the GPU. And then, so there's kernel tuning that you can do by basically playing with num threads and thread limit. There's a bunch of examples here that we have in the kernel pragmas directory. And basically, if you take a look at those, you'll see that as you modify the number of threads and the thread limit, then you'll see different usage of the registers, for instance, and the performance will change. So yeah, I'm gonna finish here. I know that I have unloaded a lot of OpenMP on you. Hopefully I didn't go too much over time, and thanks a lot for your attention. I've heard a lot of notifications from Discord as I was presenting, so hopefully if there were any questions, some of them have been addressed to some extent.
I'm trying. There are some hard ones here.
Thanks a lot, Bob.
Can you pop up for this last question? Can you pop up that slide that summarizes the map clauses, the map to always?
Yes.
I'm answering that right now, but this is a surprising thing, at least it was to me, is the clauses for map and what it does. So you do the map always. It does not copy the data if it already exists. I'm sorry, map 2. It does not copy the data if it already exists. Look at footnote 1. So if allocated, the size is checked and the reference counter is incremented. The data is not copied. And that was kind of surprising to me. I think maybe because OpenACC is a little different. So you have to add the always clause if you want to make the data move over to the GPU, or use the update clause. And I actually think that this is a good table to print out and put on your terminal if you're doing OpenMP, because it can be a little confusing. And then use that libomp target info to verify what the compiler's doing.
Yeah, and you can experiment with what Bob just said with that example mem2. Let me just find that. Yeah, so see here in this mem2 example, we are using the data environment and doing the allocation of X and Y. But if you don't do the map always before the kernel, then those will not be copied to the GPU. And so you'll see wrong results. So you can test that firsthand with this mem2 example that sits in Pragma examples, OpenMP, CXS, memory pragmas.
And we have a comment in the chat that is news to me that Godbolt is also so self-hostable, which might be a good option for sites that don't want to post their code into a web page.
Okay, I'm gonna look at the questions. And thanks for replying on the fly, Bob.
So the exercises are sort of meant to bring out some of these details. That's what, and I would actually recommend that you try those and verify on your compiler that it's behaving the way you think it should and the way the standard specifies. And even with different versions of the AMD compiler, GCC compiler, whatever compiler you're using, the NVIDIA compiler, the Intel compiler, because you can be surprised by it. And before you jump into your big code, you sort of want to understand how these things behave, how they should behave, how they actually behave, before you start really working with a big code.
So I don't feel too guilty of going a little overtime because I know that there's the break now.
Yeah.
So
We have a 30-minute break, so I strongly recommend working through the exercises from both these talks. Pick the ones that most interesting. Transpose is a fun example to try. And these OpenMP ones are really give you a much better grasp of what's going on.
okay, I think I'm gonna get the first coffee of the day. Always coming later and later.
Okay, so we'll go ahead and break until
3:30.
3:30 European time. And we'll be monitoring the chat, and we'll probably answer some questions midway through the break.
Yeah, definitely.
We're nearing the end of break time. So time to put your coffee cups down and return to the chat. We've had some good discussion in the chat.
Thanks, Bob, for leading those. Let's see if I still need my light here. Maybe.
Okay, so coffee refresh just arrived, so I think might survive. Let's go ahead and share the screen for the next presentation. I think
Yeah.
you have that one coming up, Giacomo. And this
Yes.
one will be on OpenMP and HIP interoperability. This is, I believe, a shorter presentation, although very important. And then we'll follow up with our performance portability framework, such as COCOS and C++ standard parallelism at 4:15. Okay, take it away, Giacomo.
Thanks, Bob. Yeah, so let's dive into it. Okay, so the reason why we're gonna be talking about this is because first of all, you can have interoperability of HIP and OpenMP. And also because there are reasons to use them together, which are discussed in the next slide. But before doing that, let me just say what's supported in more detail. So OpenMP can call low-level HIP kernels from the OpenMP application code. And when
It looks like the internet gods have made a statement about Giacomo's presentation, though. Give him a chance to reconnect.
Is everything okay with the audio and video? Because I was getting messages that I was muted.
Welcome back.
What, did I get disconnected?
You completely dropped out.
Oh, okay. Well, that's good that I stopped talking then. That would have been awkward. Yeah, I got a message saying that I was muted, so I stopped, and then I was trying to get in touch with anybody. Okay,
Well,
that's good because I basically didn't start.
yeah, well, Marie says one coffee wasn't enough.
I'm gonna go with the IV next. Yeah.
Okay.
Let me start over. Okay. Okay, so I was just gonna talk about the interoperability of HIP and OpenMP. So before we get into why we want to do this, let me just say what we can do. So OpenMP supports the interaction with HIP by basically being able to call low-level kernels with HIP from OpenMP application code. And when I say OpenMP application code, I mostly refer to a case where OpenMP is used to do the data handling, so the memory handling. So you're using OpenMP to map your data to and from the device and so on. And you can also have a situation where you have a HIP application code. So you're using HIP to do the data management, and you call an OpenMP kernel, and we'll see some of that too as well. And this interoperability also allows you to call the ROCm libraries from your OpenMP application code. And there's something else that you can do, which is you can interact with the underlying asynchronous stream mechanism. So here it's kind of obscured in the slide because we're not covering it in this presentation. But we have some examples in the repo where you can basically put a HIP kernel and an OpenMP kernel in the same stream, in the same queue, so that they execute one after the other. And for that, you'll have to use the interop construct that you can explore in one of our examples in the repo. So the reason why you might want to be doing interoperability within between HIP and OpenMP is that, as you've learned by now, OpenMP is in a way easier to get into, because with relatively small changes to your code, you can get it to be ported, at least in a preliminary version, to the GPU. However, OpenMP is higher level than HIP, as you've seen as well. So you have a little less, at least for now, control of the way you kind of perform your optimizations or your interaction with the thread grid. So there might be reasons why you want to port your most important kernels, the heaviest ones, to HIP, so that you can have more knobs to turn and control the performance. So there's a couple of things that you'll have to keep in mind when you're doing this interoperability thing, which are that the HIP compiler, HipCC, cannot offload the OpenMP GPU kernels. And on the other hand, the AMD compilers, such as the ones that you'll do for the offloading, such as AMD Clang, cannot compile HIP kernels. So this is something to keep in mind that we'll discuss in detail in the next few slides. Okay, so let's take a look at a situation where we have an OpenMP application code where we want to call a HIP kernel. So as I said, this is OpenMP application code because we're using the target data map to handle the data on the CPU and GPU. So here you see we are moving X to the device, and then we're staging Y to be a to from. Then there's these two functions, compute1 and compute2, that are called from the host side. Remember that after this target data, we're still on the host from the presentation that we just had. Then X and Y are modified, so we're doing the target update to copy that to the device. And then we are calling this saxp hip, which is a wrapper function that calls the HIP low-level kernel. And notice that here we have this target data use device pointer because, and this is actually something that maybe we haven't stressed enough, but one of the good things about OpenMP is that you don't have to worry about having multiple pointers for your data, one on the host and one on the device. That's handled for you by OpenMP. So basically, you use X for X on the host and X on the device. But with heap kernels, at least in the general case of discrete GPUs, you'll have to pass the device pointers to the heap kernel. So because with OpenMP, there's this unique notation, let's say, if you want to specifically pass the pointer that's on the device to the heap kernel, then you'll have to use this construct here, the target data use device pointer, and then you specify which ones you want to pass. So this is the wrapper function that we call. So see here that this sexp heap is just basically launching the kernel, and then the kernel is defined in the same file here above as just the sexp. And if we wanted to put this all together, remembering what we said before as a warning, basically we're going to have to leverage two translation units. So we'll have two separate files. One that will be compiled with HPC that includes the kernel, the heap kernel, and one that's compiled with AMD Clang++, that is the OpenMP application code. And notice here that we have the use device pointer that we have just talked about. So we can also look at the converse in a way where we have a heap application code. So see that we are using the heap API to do the memory handling with heap malloc, heap memcopy, etc., from which we want to call a OpenMP kernel. So this scenario is probably less common than the other one, but this is just to show you that you can do that as well. So see here, you don't have any data environment as you would have with OpenMP. You're just doing everything with the heap API. So once again, you have the compute 1 and compute 2 functions. And then instead of that update that you would do with OpenMP, we just have a memcopy, basically, that's copying the data from host to device. And then we're passing the device pointers to that wrapper function that this time is going to call the OpenMP kernel. So this is the function here. And so we also include this is device pointer in our pragma here. And this is quite important because we're instructing the compiler to not do a presence check and this avoids the pointer translation. So you can set libomp target info to -1, for instance, and see what changes if you don't include this in your pragma. And you'll see that there's quite a few changes that happen there. Okay, so for what concerns the compilation here, this is a makefile that was used for actually both cases. See that for sexp_heap, which is the one that includes the heap kernel, we are using HPC. And for the other files that we're compiling, we're using AMD Clang. So I don't know if it's specified directly here or through the module, but yeah, that's what we're using. Also note here that there's that line that I showed you yesterday in the portability talk that basically pulls the GFX model for you, so you don't have to memorize it, and also you don't have to supply. This is just detecting it from the machine you're on and setting it to the offload architecture for the OpenMP offloading. There's a trick that you can do to not have two separate files, but you can have them both in the same file. They'll still be compiled with different compilers, but you can have them both in the same file. And you can do that if you use the flags that basically tell the compiler to skip that part in case you want it to be skipped. So basically the code that's what we define the OpenMP code will be defined as the host code, and the heap code will be bound by the compiler if defs that define it as device code, and therefore it's skipped when you compile with AMD Clang, and it's considered when you compile with HPC. And then you have to make this copy here during the make process into a separate file before you compile. This is the other piece of the trick. Okay, so you have the two preprocessor directives that will be on the single source, and then you have to do this little trick here in the make file. For what concerns a situation where you're trying to leverage the APU programming model, such as in the MI300A, we talked about OpenMP application code, heap application code. Well, if you're on the APU, basically all the explicit memory management just goes away. So actually those two kinds of application codes kind of start to get very, very similar, because you'll get out all the maps with OpenMP, you'll get all the heap malloc, heap mem copy out with heap. So the code actually starts to look very similar in either cases. And if you want, you'll just pass the host pointer to the heap kernel, like we're doing here. We don't do the use device pointer anymore, and we just pass that single pointer. Okay, yeah, so the APU example is in our repo as usual over here. You'll just have to browse the heap-openmp directory, which has even actually more than just what I'm showing here in terms of the examples that you can take a look at. Okay, so here we're just gonna discuss briefly how you can have OpenMP call heap from Fortran, from a Fortran code. So here we have this Fortran code on the left, and remember that the heap libraries, the ROCm libraries, are still programmed with heap. So basically, if you want to call a ROC+ kernel, that's just a heap kernel under the hood. So what we have discussed still applies. So you'll have your main program here in Fortran. And once again, you'll have the use device pointers, because the ROC+ kernels still need the device pointers, just as any other heap kernel in general. This is your wrapper function, OMP dgem, that you can see here in the bottom right corner. And then at the top, since this is Fortran, you need an interface because you can't call directly C code from Fortran. So you need this interface here, and so basically see that we are covering that, leveraging the ISO-C binding module from Fortran. And this is for, let's say, what I'm discussing here is using a ROC+ kernel, but in general, you can use this approach for any custom heap kernel that you want to call from Fortran. And for the most popular ROCm libraries, there's actually, as I mentioned, I believe yesterday, an interface that's already built for you that's heapfort. So basically, you can skip, building the interface here, because that's already done for you. You'll just include or use the heapfort modules here in your Fortran code. Yeah, so heapfort is actually also mentioned in this slide. Okay, so this is the end of this presentation. We've talked about how to have OpenMP and heap kind of work together. We discussed why it'd be interesting to do it, and also we took a little look at Fortran as well, and some mentions of how the APU programming model kind of makes the whole process a little easier. That's all. Back to Bob. Thank you all.
Okay, thanks for that presentation on interoperability. And we got a short exercise time until 4:15. This is a shorter presentation, so we actually ended early. We have some questions in the chat. One of the questions is on deep copies, and we haven't put a lot of detail into the presentations on how to handle deep copies. Partly because this is fairly new in the OpenMP standard and OpenACC standard of how to deal with these pointers and structs and other similar situations. Most languages do a shallow copy and just copy the pointer and not the data that is pointed to. And many of the languages have some way to deal with it. OpenMP has added a mapper directive, and you could experiment with that for your code. It may give you better handling of those complex data types. And some of the discussion is about the differences between the HPC languages, between Fortran. And Fortran has several different types that you might encounter in these structs, like fixed size array, an allocatable array, a pointer, or even within a subroutine, different ways of passing the data in where the compiler knows the size and when it doesn't. But there's also complicating situations in C and C++ with complex structs and singletons and other cases that make this more complicated. You want to add anything on that, Giacomo? We don't really have examples on that yet, and we should be adding those.
I was just looking at our internal Teams chat because I remember talking about the mapper with Brian, who's our Fortran compiler expert in our team. And I remember that there were issues with that. As soon as I can pull them up, I'll share them.
Yeah. What makes it difficult is there's a lot of special cases that may or may not be handled by the compiler, especially since it's so recent in the standard, and it may be that the standard doesn't adequately define the behavior for some of those cases. One of the techniques that I've used in the past is define the struct on both the device and the host, and then manually map the pointers over into those structs on each side and treat it like a regular array for the transfer.
Yeah, it's always great when you work on something and then you completely forget about it. I'm finding, Teams messages that I wrote and I don't remember anything about it. Let's see.
Yeah, I'm always amazed how difficult it is for this search things to find stuff. And we have a comment in the Discord chat from Patrick that he's tried it and it's not widely supported by compilers at this time. And I think that's the case. It's so new in the standard that it may not be in every compiler. And it may be in the C compiler, but not the Fortran compiler. If we get a reproducer, we'll push it by our Fortran compiler team for the particular case you're interested in. It does take a while because we often have to get a 3 or 4 people to look at the standard and determine what it really says.
So I had a Teams chat with my past self and I was able to jog my own memory. So it looks like when I tested it, I was trying to use it with C++ in a way that basically you have a class that has private members and then you modify those with the get and set. But the mapper wanted them to be public and accessible with just the dot. So if I had them private, then it didn't work. So I think that was what turned me off with the mapper for C++. I don't think I used it for Fortran. Don't even know if at the time it was included in the compiler. But I think Brian said that they were working on it. And yeah, Patrick, I think you might want to experiment with the enter data and exit data constructs rather than the mapper. At least for C++, that's what we've played with. Let me just drop the examples in the chat.
Yeah, and I've done this in Fortran, but what I would do is do a regular copy of the array over and then do a array assignment into the pointer in the Fortran struct on the GPU side. But it would clean up the code. I think there's also limitations on the effectiveness of this mapper directive. I tried doing it for a 2D array to map the rows into the struct in C, and it requires way too many lines of code to make that work. I'm hopeful in C and C++ we'll see MD span come in with the multiple dimension arrays, and maybe there's a way to start leveraging that and mapping over multi-dimensional arrays without using something like a mapper. Okay, Giacomo's posted example. Okay, let's go ahead and work on exercises. Do we have a read on if people are having difficulty getting on AAC6 this morning or this afternoon? We had some issues last night, somebody messing with the system on our side. Not our team, some other team.
Yeah. Yeah, I asked Amos. Let's see if I can get some feedback. I didn't find anything wrong where I'm looking at, but more than one person that was added last night said they couldn't get in. But after I added them, I logged into their accounts with sudo and looked like everything worked, but now I can't use that same procedure. So something happened when I was sleeping, when we were sleeping.
If you are on the system, there is an 8-hour queue time limit, but it hasn't been properly enabled to cancel jobs after 8 hours. So we have a few people that have been on for a couple days. You might check and make sure that you haven't tied up a GPU for that time. At the end of the workshop, I will kill those jobs that have been running for multiple days, but I will leave them for now so that you can jump on those nodes. But do check and exit your allocation if you're not using it. Okay, getting ready for the next presentation. So you've all made it through almost to the last presentation at day 2. Congratulations. It's a lot of material. So we're going to show a different kind of language, these higher level frameworks of performance portable language such as Cocos and Raja, and then also look at standard parallelism that is just starting to get into some of the compilers. In this case, we're looking at C++ standard parallelism. These languages originated out of a concern that porting to the GPU was not performance portable. And so an initiative in the Department of Energy, the DOE in the US, started a bunch of workshops and conferences on how to address that. It was widely accepted that really was not sustainable to have custom implementations for every vendor for GPU versus CPU, that we really needed to have a single source for application codes. 2 of the popular PPP languages that have emerged are Cocos and Raja. They're both good systems, and actually there are several other languages that use the same concept. There's OCCL, OCCL, and YACL, yet another kernel language, and other applications or application niches have developed their own tools that follow this sort of approach. So COCOS is more of a comprehensive approach that implements these performance portable language. Raja is more modular in structure and is used at Lawrence Livermore National Lab. They both share a lot of the same ideas, and in fact, there was a lot of cross-fertilization between these two teams on how to implement these layers and get performance. Both of those are great choices, and both are well supported for AMD GPUs. We have staff members working on the Raja kernels to make sure that the performance is good on the AMD GPUs. And we have been working very closely with the COCOS team on the AMD GPU port that they have. So why COCOS? Why these performance portable languages? For C++ applications, they're very attractive. They hide the vendor-specific code from the application, so application teams, after an initial look at these languages, have found that it makes it much easier to develop code that's cross-platform. In fact, codes that have been using COCOS when the AMD GPUs came into play at Oak Ridge and other places, the application code teams did not have to do anything. COCOS just implemented it and it worked. Similarly with the Intel GPUs at Argonne. So it greatly simplifies how to write code for an application. It does provide a little bit of an opaque layer on top of the program, so it's a little bit trickier to understand what's happening and to debug it. But that's the trade-off that you have. COCOS started at Sandia 10 years ago, and it's now a worldwide supported tool. In fact, from talking with Sandia team, there's a lot more contributions from outside of Sandia at this point than within Sandia. It was part of the Exascale Computing Project, and it's been a key player in the High Performance Software Foundation, which is the follow-on to the Exascale Computing Project. So there's still good support for it. This is not one of the languages that you have seen that was developed by a graduate student and will disappear when they graduate. This is going to be sustained for a long time. And COCOS code performs quite well. They pay a lot of attention to the details, things that you're probably not going to be able to do in your application. You're just not going to have time to do that. But it does mean that there's an abstraction layer that makes it a little harder to see how that translates to the hardware. COCOS has had a hip back end from back when these were graphics cards, and in 2022 it was promoted to production status. So it's been actually in COCOS for quite a while. They actually added a GFX 942 _ APU backend for the MI300A. So that gives you a single memory address for their for their arrays. Kokos is a Greek word for grain, seeds, or kernels, so that's kind of appropriate. And it's based on C++ templates. All of these frameworks are really leveraging C++ templates and lambdas or functors. And the reason this is so effective is you can implement a library much quicker and distribute it. Trying to get that to the compilers, every compiler is going to take a lot of time. So libraries are just easier and quicker to implement new ideas. And Kokos is successfully migrated their multi-dimensional array techniques and specification into the C++23 standard. So we may finally get a multi-dimensional array once compilers start implementing that. It's a well-developed concept, so it should be fairly quick for compilers to implement that particular feature. So there are many backends for Kokos for the CPU and the GPU and all the major GPU types and CPUs, parallel CPU languages. So to understand the abstractions that are in Kokos, we have to fall back on that all these languages have to deal with two basic abstractions. One is execution capability, so how to generate and specify the execution of loops and similar code on the target architecture. And then there's also memory handling. So how do you allocate it? What level of memory are you working with? When do you move it? On the MI300A or with the APU programming model, the memory handling can be greatly simplified in all of these languages, and in particular in Kokos. So let's see how Kokos deals with those two issues. So in execution spaces, which is what they call this abstraction, they are abstracting the compute hardware, and they have three execution patterns: simple loops, reductions, and scans. Now, scans were missing in the OpenMP standard. They have recently been added to fill that gap that they did not have coverage for. Execution policies, you can specify the index sets that are to be operated on. And all of these concepts, we're separating the body of the loop from the index set, because the index set is going to be specified on the host, and the body of the loop is going to be sent to the GPU and executed there. Team policies allows us to leverage things like LDS and have more hierarchical parallelism where we need it. Memory spaces, so that's going to specify what level of memory we're at, different types of memory allocations. And then one of the particular things that Kokos does is switch or have layout right and layout left. And it actually does a conversion between the two, going to the GPU unless you specify otherwise. And then there's also memory traits. These are special cases: atomics, random access, and streaming stores. Kokos has really heavily leveraged CMake. And so there are two ways to build Kokos: one with an external build that you can even load into a module, or an inline build, so you can put this into your repository. I would recommend as a submodule, and then build Cocos at the same time that you build your code. Cocos builds extremely fast because it's basically templates. So there's not a lot of heavy compilation that has to be done for Cocos. And we'll show two examples, the first one with an external Cocos build and the other one with an internal Cocos build. And I think this presentation will only show one of them, but there is, you can look at the examples in the example repository, and there are directions for the other one. So this is sort of an intro to Cocos, sort of a hello world first step kind of view of Cocos. There is excellent documentation on the details of Cocos that the Cocos team has put together. So we're just going to make you familiar with it and get a first program to run with it. So here are the steps we're going to go through. It's fairly short steps. And we have a Cocos module on the system that we can use instead of building that external Cocos. So the first thing you do is we're going to load AMD Clang and ROCm and clone the Cocos repository. And then we're going to execute this command to build Cocos with the OpenMP backend. Now this one uses Vega 90A architecture, and it's used in this example because it's fairly portable. There are architecture types that are more specific for the MI300A and the MI200. It's a little confusing at times because you have to specify the compiler to build Cocos with, and that can be different than the compiler that is used to build your application. And so we specify HPC for the application here. And then we export that Cocos dir, and we're ready to go. So we start modifying the build in this stream triad example. And it's pretty easy to do this in the CMake list. We're just going to do find package Cocos required and then add our linked libraries to our executable. So now we have the build changed to include Cocos, but we have to go and deal with the source code and convert that. So we add this include file at the top of our source code, and then we add this initialize and finalize. And this is a scoped pair. So you see the braces at the start and the end. If you don't have the braces, you're going to get some errors at the finalize of things not being deallocated properly. Then we create Cocos views, which is their syntax for creating arrays. And you can name these arrays, which is kind of convenient if you're debugging. In this case, we're showing a single dimensioned array, but you can allocate multi-dimensional arrays as well. So we do that and we rebuild and run. We haven't specified the compute directives yet. So this is just providing the structure for the initialization of Cocos, and then how to create a memory, Cocos memory, or views. Data in 1D can be accessed with either the square braces or the parentheses, and Cocos will handle the deallocation automatically. By default, the views are initialized, and so you may want to include this view allocate without initializing to avoid that initialization. And then you can create what they call an unmanaged view of a pointer that already exists in your program. So this is a way to adapt your code step by step to use already existing data. So now at the we're going to implement that parallel 4 execution pattern. And we simply add the COCOS parallel 4 at the start of the loop and close off the loop. We have the COCOS lambda, so this is going to be a lambda expression which will separate the index set from the body of the loop, capture the data that needs to be transferred over, and that's how it's going to automatically move that loop over to the GPU if we're using the GPU backends. So that's really all you have to do in that source code is just change that parallel 4, but this is a pretty simple program. We can also add COCOS timers, so that's optional. I show here, how do we replace that, and the examples show that as well. And so this is our completed version of the COCOS stream triad. It's very readable to even application programmers which have not seen COCOS before. We see initialization parallel 4 loop. We see the parallel 4 loop in the that we're repeating multiple times to get a timing on it. So in the simple example, it's not that difficult for somebody to understand what's happening. That's important because we may have somebody coming along maintaining this code, who is not intimately familiar with COCOS. We can do performance profiling with COCOS with the COCOS tools. These are fairly simple but very powerful. So we can create those tools. We have to separately build them, and then we can run the application with the tool. And following running the application, we can then print out the results of the tool. And it's just going to give a list of what's taking the most time. It's a fairly simple presentation of the profiling results. So we've shown how to go step by step in a very simple application to add COCOS into it. And we've seen how to do a parallel 4. In the next example, which I think we're skipping in these slides, we do a 2D array and show reductions and other more complex operations that you may encounter. But we're going to jump over to C++ standard parallelism, and that in ROCm it's called HIP standard par, HIP stand par. It was implemented in a few months ago and implements the C++ standard for standard parallelism. It does not have the latest C++ standard additions to that capability. So we're going to go through just this, how you can use this. It's fairly early in both the standard and in the compilers. And so it's not what I would recommend for if your code is really trying to reach the absolute best performance. But it is very interesting for simple parallelism in C++ code. So basically what this implements is C++ standard library has a bunch of things called algorithms. And I'll show you a big list of those in a couple slides. But with each of these algorithms, we can supply a policy. And these algorithms, again, use this lambda expression. So they're going to capture this return 5 times each element of X and send that to the GPU or the CPU if we specify that as our backend. So in this case, we have no policy specified, so it's just going to run it in serial. The policy types that you can have are sequential, unsequential, par, and par unsequenced. Unsequenced is kind of an awkward way to say vectorization or multi-threaded. multi-threaded and vectorized execution. But this is the policy that AMD has implemented, par on sequence, because it gives us multi-threaded and vectorized execution on the GPU. Now, not every type of code in that block is supported. For example, memory allocation and deallocation, and a few other cases that we're not listing here. The back end is basically going to use the rock thrust library and use that to execute on the GPU. So there is a blog post on this, and it actually works also on the workstation GPUs through some tricks of replacing the memory allocator throughout the code. And so there's a lot of parts to implementing this: the compiler, rock thrust, and some compile flags that you do in your application. And it really is very effective when we have this automatic memory management with HSA XNAC. Without that, we replace the allocation in the code so that it will run even if we don't have that. So here's a couple examples, or we'll step through one example here of a serial code running it on the CPU using TBB library. And then on the GPU, we change that policy to par on sequence and specify this compiler flag hipston std par. And that's going to tell it to run on the GPU. And so this is basically data parallelism that we're going to be doing. And if you use standard algorithms in your code, this is a very simple change. If you've got explicit loops, it can take some effort to convert it to using standard algorithms. So this may be more of a code change than you would want to do in a complex application, a large complex application. And similar restrictions that you would have that for doing parallel threaded code apply here. So we have to be careful in this example at the bottom of the slide. We could have a race condition here. So we have to be aware of those kinds of situations. Okay, so this is showing that transform operation running on the AMD GPUs with that flag. So there's a lot of restrictions. I'm not going to go over all of these just for the sake of time, but you do have to watch for some cases code that is not going to be able to be operated on the GPU. If you're compiling this for the workstation GPU, where we replace that allocation in your code, there are some additional restrictions. This is actually kind of a slick way and kind of gives you a hint that in your regular HIP code, if you use a different type of allocation, you can actually run on your workstation GPU. Here's a full list of the C++ algorithms that are supported. There's a lot of them. I don't think any of us would know about all of them or ever use all of them. But it is a very large set of algorithms that are supported. And if you want to walk through these examples, they're in the examples repository as well. And we can run that SAXP transform, or with the reduction. We're going to move on to so this is for each algorithm. So transform may be confusing to a lot of people seeing it in the code. So there is a for each, but there are actually slightly different cases you would want to use those. So here's an example of the make file that is being used. And there are some changes depending on what version of Rockham. And we have to supply a few additional compiler hints to get the right paths. So we talked a little bit about par unsequence already. So this is a lambda expression, and so there's details in here that may not be apparent just glancing at it. We need to, for the reduce, we need to specify that it is a sum and that it is initialized to 0. And then we can do the reduction operator. So here's a traveling salesman problem. It's kind of an interesting problem in computer science. And this is being solved by brute force. And if we just change in the example code execution par to execution par unsequence, this will run on the GPU. And we can look at the results from that. So as you get larger and larger number of cities, it can take a lot more time. So here the CPU version is using all the cores, and there's quite a bit of speed up when we do that. Here's a minimax problem, which is a space filling algorithm to pick the point to be added to minimize the maximum distance from any point in space. And we'll look at the performance for this one. So the original sequence, unsequenced par, and par unsequenced for 4,000 elements, we see a modest speed up, but this is not that big a problem. One of the tricks here is that we have specified not using all the cores on the CPU because there's just not enough work to really leverage all of them. And as we increase the number of elements, we see that it's actually the runtime is quite long on a serial, and we're seeing a significant speed up with the par unsequence. And then we have to add, we can get a little bit better performance if we add affinity. So it's an interesting option for C++ code, and certainly for getting modest speed up and parallelism on a GPU. One of the reasons we're presenting this is to see the contrast of the standard parallelism with something like a Cocos parallel 4 approach, which may look more familiar for HPC applications. Each has a place they may get used. Right now, C++ standard parallelism is really quite good for like a 1D array of list of particles or cells. It gets a lot more complicated with 2D grid indexing, where you're not operating on all the elements of the array. For example, when we have halo or ghost cells, that becomes much more complicated. And that's the end of that presentation. So we've got about 10 minutes that you can work on those exercises on your own time. But at this point, I'm going to go ahead and wrap up the presentations for today. And so any quick questions in the chat?
There's a question about recall, and I actually just asked one of the people in the team, and they told me that we want to maintain the same API as Nicole.
Yeah.
And even if they will move away from it in the future, they still plan to provide a compatibility header file.
Yeah, there is a strong emphasis on making portability easy from existing codes that have used NVIDIA, even though the underlying software may vary quite a bit. Having the same API allows a quick portability. So they try not to get too far away from the behavior of CUDA.
Yeah, and someone asked how to basically select which backend you want for OpenMP and HIP, and I pointed them to our script to install HIP, to install Cocos in our HPC training doc repo. And Gabriel mentioned that, in fact, in the script, there's enable HIP and enable OpenMP, but enable OpenMP is for the CPU and
Right.
HIP is for the GPU. And I think they have added support to do OpenMP offload for the GPU for the backend, but last time I looked into it, I had some issues. I still have to go talk to myself on Teams and see what I said about it. But I think there were some unexpected failures that we saw when we tried that. It may have changed now with newer versions.
Yeah, so the idea with Cocos is that you can have a serial in a single backend build of Cocos, you can have a serial, a CPU parallel, and a GPU language specified. I do think I've had some problems with specifying both the parallel CPU and the parallel GPU with builds, but that's the basic concept, is that you could have all three in a single Cocos build and specify those in when you build that version of Cocos. Yeah, and we'll follow up on this Nickel, Rickle, and CocosCom. We'll talk more about that with in our MPI talk, I believe tomorrow. Okay.
And I've got more on Rico from Shelby from our team that says the APIs are the same, so their source code wouldn't change, but the default environment variables will change from Nickel to Rico. If they plan on incorporating some of the environment variable setting into the wrapper, those pieces would change from Nickel to Rico.
And what we'll talk about with MPI, a lot of applications use MPI, but you can mix MPI and Rickle. Rickle implements some very fast collectives for the AI packages. Okay, so we'll wrap up, and we'll monitor the chat for issues and for questions. If you have trouble getting on the AAC6, please let us know in the Cloud Resources channel, and we'll see if we can resolve them. GPU 60 is a separate system, so you can also try there. It's an MI300X, but it's just a single node, so it will not handle quite as heavy a load. We'll wrap up, and Seema and Marie, do you want to close out for the day?
Yes, actually, yeah, I can close it.
Okay.
Seema has a little bit problems with connection, so I'm very happy to close it. Thank you everyone for attending our second day of AI AMD training, and looking forward to see you all tomorrow. So prepare coffee and fingers.
Yes, and come back and see if Giacomo's voice will last for 3 days straight. The suspense is killing me.
I've got a lot of honey.
Thank you all.
Thank you everyone. Have a good afternoon. Bye bye.